In previous lectures, we discussed the geometries of Dubin's paths, and we also discussed the path lengths of each of the 4 individual possibilities. In this lecture, we're going to now discuss the path management for executing a Dubin's path. We'll develop switching conditions for switching between the arcs and the straight lines. We'll also define the parameters for each type of the Dubin's paths and present an algorithm for managing them. So let's go ahead and get started. If you recall, we have our Dubin's path that goes between 2 oriented waypoints. So the inputs to defining our Dubin's path are just our starting location, starting direction, ending location, and ending direction. From those, we'll calculate, we use just the 4 possibilities, and we'll end up with a starting circle location, ending circle location, as well as the ending circle direction. Now we have to choose when we're going to switch, right? Because we're going to be executing an arc, straight line, and an arc. And we want to have the robust switching conditions like we did with the straight line paths and the arc fillets. So what we're going to do is we're going to define a half plane. We're going to let Zi be a point on the switching plane. And so this is a point on the plane. And there's an infinite number of these points that we could choose. 2 of them are very obvious. One is we could choose for Z1, we could choose it as CS because the boundary actually includes CS. A second choice is we could actually define Z1 to be on the path. And we're going to define our Z's to be on the path, even though we could use the center line. The second thing we need to define for each one of our Dubin's paths is the normal vector to that switching surface. So we'll let Qi be the normal to the switching surface. Excellent. So we'll define that for switching. So H1 will help us switch from our arc 1 to the straight line. H2 will help us go from our straight line to arc 2. And H3 will help us go to a new path. So our following Dubin's path. For example, we could have this come off and go right, straight, and then we don't have a lot of room, so we'll quickly turn. Oh, that was a left at our first, and now we'll turn right. So we'll have our next Dubin's path that we need to execute. And I didn't draw our radiuses super well, but we'll have another Dubin's path that we're going to execute right afterwards. So H3 helps us transition to that next path. Okay, so we're going to go through path type or case by case and define what each of these Zi's and Qi's are. To start off, we'll look at again our RSR, which is kind of our simplest path that we've done. We defined all the geometries for this one. We should be good to go. So let's review. We're going to be switching at this point. So this will be our Z1, and we'll let Q1 be the vector. So Z1 is the point, remember, and Q1 is the vector pointing along that, is orthogonal, or is the normal vector for our half plane, which just so happens to also be pointing along the path. Then we'll switch out of it, and the geometries are not super nice because these 2 lines should be parallel. We'll call this point our Z2, and again, the line that's orthogonal to that is still going to be, we'll call it Q2, but it's always going to be equal to Q1. Okay. And then we'll have our third switching condition, right? And this one will be Z3 is just equal to our ending point. And then we'll define Q3 based on our ending orientation. All right, so let's go ahead and jump into it. Q1 is perhaps the easiest thing to define because if you recall, the line between our center points is parallel to the line that we're going to be traversing. So Q1 we can just define in terms of our center points as we're going to be our center end minus our center start, and we'll divide by the magnitude just to make sure that we have a unit vector. So we have CE minus CS. Okay, so we have Q1, and now we're going to define that point Z1 that's on that half space. So again, we're switching once we get to that half space. This allows that robust. Once we hit that line, then we'll switch to, once we hit the plane, we'll switch to executing the line. So we'll let Z1 be equal to our C, oh, and I missed, I should have had an R, right? CR start, and we could leave it like that. In terms of defining the switching, that's going to be a point on the boundary of the plane. But we're going to add a little bit more just so that we can define a point on our path. And again, that'll help us when we're commanding the line. Now we have a point on the path. So we have it, we're going to have our radius. And I'm going to define this, I'll write it down. We'll have our rotation of Z, a negative pi halves, and we'll multiply that by Q1. All right. So that's going to be the point. Let's talk about it. This vector right here is a unit vector. So we're going to be a distance. So when we multiply it by R, we're going to be a distance of R from the center. So basically that's where the line is, right? So, or where our point is. This distance right here is R. Now I'm going to rotate Q1 by negative pi halves. If you recall, all the way back in chapter 2, we talked about active versus passive rotations. Our passive rotation we used for rotating coordinate frames. Active is we're using for doing our coordinate, or for rotating a vector itself. So we want Q1. We know that since this is orthogonal, we can use Q1 to define the vector pointing, and let me draw this in red, pointing from the center to that point Z1. So Q1 will help us define that direction, and really we want to move, we want to reorient Q1 by a negative pi halves direction. Now recall that since this is an active rotation, our rotation matrix, to make life simpler in terms of we're wanting to rotate it by that negative pi half, so we want to keep that same convention. Our active rotation matrix, let's just write this out, RZ is going to be equal to, we'll have a cosine, and we'll have the negative sign up top. And then we'll have our sine by 0, cosine, and we have 0, 0, 1, 0, 0. So when we're talking about these active rotations and we use RZ, keep in mind we're putting that negative sign in the front. So this is different than when we're doing passive rotations, right? Because the active rotation is equal to the transpose of the passive. Okay, so that allows us to come in and just easily rotate Q1. We know we want to rotate it up by an angle of negative pi halves. So when we do rotation of Z by negative pi halves, we're going to end up getting, we'll have a cosine of negative pi halves, a negative sine of negative pi halves, a sine of negative pi halves, a cosine of negative pi halves, 0, 0, 1, 0, 0, which is just equal to, and cosine of pi halves is just 0. Sine of pi halves is 1. Sine of negative pi halves is negative 1. And taking the negative of that, we'll just get a 1 out in front. So we'll do a 1. We'll get our negative 1 down here. We'll get a 0, 0, 0, 1 right there. Okay, and just to gain some intuition, say we have our vector, say we have our vector E1, right? E1 is equal to 1, 0, 0, right? So it's pointing in the north direction. So it's pointing up. Okay, if we rotate it by RZ of negative pi halves times E1, it's just going to pick off that first column. So it'd be 0, negative 1, 0, which is pointing, after we've rotated it, is pointing in the negative east direction. So we get some intuition there. So if we were to start off with E2, right, RZ of negative pi halves times E2, that would be equal to, we'll just get the second column, be 1, 0, 0. So in other words, our E2 would go from pointing in the east direction, get rotated up to pointing in the north direction. So just want to make sure that you're very clear that when we're writing RZ in these lectures right here, we're talking about an active rotation of our vector. So you have to be careful. The negative is in the wrong spot according to chapter 2, right? Not the wrong spot. When we defined RZ in chapter 2, we have the negative in a different spot, but that was because it was a passive rotation. Okay, excellent. So we're going to take Q1, we're going to rotate it back by pi halves, multiply it by r to give our radius, and that gives us this distance there. So that's Z1. Excellent. So now we can come in here and we can define the Q2 and Z2. Remember that Q2, it's always going to be equal to Q1, so that there's no need to define anything else. And then we'll have Z2, and Z2 is going to be defined very similarly. We have CRE, so our end center for the right circle, and we could leave it like that again. So that's going to be a point on the boundary of our half plane, but we'll define it as being on our actual path. This one isn't so necessary to define on the actual path, but we'll do it anyway. We're going to get, again, we'll do our negative pi halves times Q1. So this will rotate our vector. Well, let's draw in red. It'll go, our Q1, right, is pointed straight along the line. We'll rotate it up, and we'll do R times our rotation of Q1 to get up to Z2. Perfect. Now, let's jump into Z3. Z3, we have two choices. We could just use the center again, but might as well use the endpoint. That's defined before the center point anyway. So we have our endpoint, and our Q3 we're going to define as equals to C, our chi sub E, sine of our chi sub E, and 0. Right, that's just a unit vector in the direction of chi sub E. Now the book writes this slightly different. This is just equal to RZ times chi E times E1. So we're just picking off that first column of the Z rotation matrix. Excellent. So we have, and where we've defined, right, we're just taking off that first column of that matrix. So, and this is nice because it allows us to easily write it just on a single line. So there we have it. For RSR, we have Q1, Z1, Q2, Z2, Q3, and Z3. Okay, and don't forget we're using an active rotation for our RZ definition here. Okay, let's jump into our second one. Oh, there we go. So in our second one, we'll define things fairly similarly. If you recall, now we're going to be, our direction isn't quite as simple, but we're still going to be defining a point Z1, point, and a direction Q1. And then we'll define our direction Q1 or Q2, right, because they're equivalent. and we'll define a point on there called Z2. And we'll define here our third switching surface. We'll define that as Z3 with the vector pointing out as Q3. Okay, so let's start jumping out and defining things. So we know again where the center point is. Let's switch our colors. We know where the center point is. This arg theta, sorry, couldn't think of it for a second. Arg theta 2 is pointing along a vector that points in this, oops. Let's see, arg theta 2. There we go. So arg theta 2 is pointed that direction, right? So it's going to be, hold on. Sorry, I misread my notes. Okay, so we have arg theta 2, and it'll give us this vector that's pointed in that direction, right? So we want to go from our center to Z2 along that vector. And a cheap and easy way to do that, to define this vector, would be just to be RZ arg theta 2 times E1. So basically we're just rotating up our vector E1. We're rotating it down to be where V2 is pointing. I did not state that very well. Let me come back here and just state this one more time. So we have arg theta 2, which defines the angle to where we're going to be going to the point where we switch, right? And so we can take a unit vector in the direction of that angle. So that would be, we could take cosine arg theta 2, sine arg theta 2, and 0, which is just equal to, again, RZ arg theta 2 times E1. So that's what we're going to do. So we say that Z1 is then going to be equal to our center point plus, and again, that's where we could stop because that's going to be on the half plane. But then we're just going to define the point on the line, which is going to be R times RZ times our arg theta 2 times E1. Excellent. And then we'll have Q1 just be equal to, we're going to rotate the vector that points to that arg theta 2. We're going to rotate it so that's that pointing in that direction. We'll call that Q1, right? So we have our RZ, we're going to do arg theta 2 plus pi halves, and then we'll multiply that by E1. So we're just rotating these vectors around. Okay, Z2 then is just going to be equal to, let's write this up. We have our left end. We're going to do a very similar thing where we're just multiplying R times RZ, and then we have arg theta 2 plus pi times E1. Because remember, now when we're joining the path, we're pointing along a vector that's in the opposite direction. So let me draw this up in green. Opposite direction than we had before. So that's where this plus pi comes into play. Okay, times E1. And then we have our Q1, which is nicely defined as Q2, which is nicely defined as Q1 because it's pointing in the same direction as Q1 was. Excellent. Then Z3 is always, we can just define it as the endpoint, or we could define it as CLE, right? And then Q3 is always defined the same as well. We'll take RZ of our chi at the end, times it by E1. Okay. So we have now two of our cases broken down where we've defined all of the switching planes for those two cases. Let's jump into our third one. Again, we have our switching plane. So this LSR, we're going to be switching at the point Z1, and we're going to be pointing along Q1. Then we're going to stop right here, even though the angle isn't drawn quite correct. We have our point Z2, and we're going to still be pointing out at Q2. And we'll then switch to the next Dubin's path when we're right here. So let's call it BQ3 and point Z3. Okay, so let's go ahead and define each one of these things, right? So we can say that Z1 is just going to be equal to, now we're going to do the CLS, so we're starting in the left center at the start. Then we're going to add in R, and we're going to multiply that by RZ. Again, we're doing that same trick, or we're just rotating around that our x-axis. We have rho plus, we'll do rho 2, and call that E1. Now I want to just look at this. I don't quite like how the book switches the notation slightly in terms of defining rho, I call it rho, arg theta 2, sorry, and arg theta. So they define arg theta as 2 as the angle between the line going between the centers and now the point of departure. Where previously it had always been just the point of departure. So that's why we have arg theta plus arg theta 2. Okay, and then we have the direction. And the direction is similar to before. We're just going to take the vector that points out there, right? So this is the vector that points to that value. And we're just going to correct it by pi halves or negative pi halves. In this case, we're going to come back by negative pi halves. So we'll do RZ times, and we'll do our var theta plus var theta 2, and then we'll subtract off the pi halves and multiply that by E1. Okay, Z2 is going to be defined in a very similar way. Again, we're switching sides of the circle, so we're going to be taking off from the red angle, from the red line that we drew up there to this green line. The difference there is just we're going backwards by pi. Oh, I shouldn't draw from that line, but we're going backwards from pi to get to the green. So we'll define point Z2 as we have CRE plus R times our RZ, and we'll have our arg theta plus arg theta 2, and we'll take off that pi times E1. And then we have, as always, we just can write Q2 is equal to Q1. We have Z3 is equal to PE, and Q3 is just equal to, and we'll do our trick where RZ, take our end orientation, and we'll multiply that by E1. So we can write it on a single line. Okay, excellent. So now we've gotten case 3 out of the way, right? So now we can define all the points for the switching surface for case 3. Case 4, it's going to be very similar to case 1, right? Where now, again, we're switching at point Z1, and our point Q1 is parallel. So it's in the same direction as the line that goes between our center points. Then we'll end here at Z2, and Q2 is still that same vector. And then we have our, oops, didn't draw that very well. I don't like how these look like they're the same line going up and down, but they're not. So we'll have our point Z3, and we'll use that angle to define Q3. So again, Q1 is just equal to the same as it was for the RSR, sorry, didn't mean to mess that one up. So we have CLE minus our CLS all over the magnitude to make it a unit vector. Our point Z1 is then we can take that and just rotate it. So we have CLS, our starting center, plus R times our RZ. So we're just going to use our rotation trick. This time we're going to rotate it by pi halves instead of negative pi halves, right? Because Q1 is pointing along the line, and we want a vector that's pointing an additional pi halves. So we got plus, we have that pi halves times Q1. Okay, then we have Z2 is equal to our center point plus, and we'll do the same rotation to get to Z2, right? So we're still doing the same thing. It's a parallel line. Okay, and then we have Q2. This one's always the easiest, right? It's just equal to Q1. And well, I don't know, Z3 is pretty easy too, PE. And our Q3, whoa, that was a funky Q3, is just our same trick with our ending point times E1. And I just got that, wrote that all in the, so I'll write down Q3 down here. Just the same as always, RZ, and then we take our ending orientation and we multiply it by E1. Okay. So now we've defined these switching surfaces for all four of our cases that we're concerned about. And again, we haven't defined them for the other two cases because we're assuming that we have sufficient spacing between our points. So now let's jump in and look at this Dubin's path algorithm. So right here, they had made sure that the length between the starting and ending points was greater than 2r. Realistically, or greater than 3r. Realistically, we can do a 2r and we'll be just fine. Okay, so this first portion of the algorithm is we're just calculating our centers. Right, and if we zoom out, we're just calculating the starting center, so we'd calculate both of these centers, and our ending center, we'd calculate both of these centers. So we're just calculating both of our centers, or all four of our circle centers. And then we're going to compute L1, L2, L3, and oh, that should be an L4. Using the equations that we've already developed. And these equations are for just calculating the path length. Now, I don't quite like how this notation is written. So we're doing argmin of these four things is equal to 1. So in other words, L1 was, this is our RSR case. And so if you were in, this assumes 1 indexing. If you're going to be doing it in Python or whatnot, this should be a 0, right? And similar, this would be a 1, this would be a 2, and this would be a 3. So if you're 0 indexing, it's going to be 1 greater. So anyway, all it's just saying is that if RSR results in the shortest path, then we're going to come in here and we'll say that we're going to define all of our path parameters. So the starting circle is clockwise and the ending circle is also clockwise, right? This is our R component, is we're doing a right circle, so we're going clockwise. So we're taking the right circle, on both the start and the end. We define what Q1 is. We define what Z1 is based on Q1, and we define what Z2 is based on Q1. Now you'll notice that we're missing a couple of things here. First off, we've not defined what Q2 is, and we haven't defined what Z3 is or Q3, right? In fact, if you come up here and look, Q2 is missing. Well, that's pretty simple. It's because Q2 is always equal to Q1. And we do have Z3 and Q3 as some of our parameters, but we just define those here at the end, right? Because they were always the same. So we're not missing those values. Q2 is just equal to Q1, and Z3 and P3 are always the same value. So there you have it. So now we can define based on these things. These are just these are the equations that we discussed already for switching. Excellent. So those equations we already went over. Then if the shortest path was instead path or L2, this would correspond to RSL. This guy down here, let's just write them all out. LSR and LSL, so that we don't have any confusion there. So let's just go through this just a little bit again. So RSL, so the first circle is clockwise, the second circle is counterclockwise, right? So that just a review of the notation, what those lambda variables mean. Again, we come in here, these are the equations that we already defined. And what we end up calculating are our Q1, Z1, and Z2. Okay. Similarly for LSR, now we have both, we start off counterclockwise and end clockwise. And then we come in and calculate Q1, Q2, and Q1, Z1, and Q2. Then similarly for LSL, right now we're doing counterclockwise on both of our circles. We're doing the left circle for each one. And then we define Q1, Z1, and Z2. And like we mentioned before, we always define Z3 and Q3 the same. Okay, so this will allow us to define our Dubins parameters. We can calculate the Dubins parameters, just come in here, figure out which one is the lowest cost, and calculate our switching planes and parameters accordingly. Okay, now this final algorithm is how do we follow the Dubins path? So we can come in here and define the following mechanisms, right? So the first thing to note, and I wish this was drawn slightly differently, is that just because we want to switch at Z1, Q1, right? Where Z1 is that point and Q1 is pointing along the vector. So we want to switch there. But what if P start was right here? That's a perfectly valid configuration. If P start was right there, and this would be then our negative chi start, then we'd want to execute this circle for the first part of that half plane. And this will happen from time to time where we start off, basically starting off on the wrong side of the half plane. Of this half plane. So we're starting off on the wrong side, so we don't want to trigger our starting condition. So if we come over here and look at these states, we have more than 3 states, right? We have, it says up to state 5. Okay, that's because we're going to do our state 1 is going to be our first, well, let me write it out in a number. The first part of the first circle. State 2 will be the second part of the first circle. State 3 will come in here and we'll actually execute the line, right? So state 3 is the line. State 4 is similar to state 1. We're going to do the first part of the second circle. Because as we come in here, here's the line that we have to switch out, and how it's drawn, I don't like this line, but we could start off in the wrong half plane. So if we started off right here, we could be on the opposite side of H3. And so in that case, we'd want to make sure that we execute the arc before saying that we're finished, right? Before going on to the next Dubin's path. So we'll execute the first part of the second circle, and then in state 5, we'll do the second part of the second circle. Okay, so we're going to have those 5 states. Okay, so let's come in here and look at this algorithm, right? So we come and we calculate our Dubin's parameters. So at this point, the algorithm below this, it doesn't care what Dubin's path we're executing, because it's always going to be arc, straight, arc, right? So in that case, it's kind of nice that we ignored the arc, arc, arc examples. Okay, or possibilities. So again, we're going to come in here and we're going to do the first of the first arc. So we come in and we define this flag variable. Flag equal to 2 implies orbit, and flag equals to 1 implies a line. So that's just all that this flag is denoting. It's denoting is it orbit or line. Okay, so if it's state 1, we're going to be doing an orbit, and we just send out, if we look at the outputs of this guy, we're going to be doing the flag, so is that orbit or line. R is going to be a point on the line. Q is a direction along the line. So these are our line parameters, and these guys right here are orbit parameters, where C was the center point, rho is the radius, and lambda is the direction of travel. So we come in here, we've calculated all of these things in the Dubin's parameters, right? And so now we just push out the starting circle. So we push out the starting circle, and then we check our condition. So this is our switching condition. We switch, and the one thing to notice is this negative sign. So this will take us to state 2. It's just basically saying that we're pointing in the opposite direction, right? So we want to make sure that we get to this side of the half plane before we switch, before we decide that we're done with our arc. So we first get into the negative of H1, and then in state 2 we'll worry about getting into the positive of H1, right? So it's a positive Q1. Okay. So again, we come down here. So we'll switch to, let me write this, switch to second of the first circle, or first arc. Okay, so now we've switched, and we're still going to continue to execute the same orbit parameters. So I think if we were actually write this out in code, we'd still have to have these same parameters down here. This now is, the state 2 is second of the first arc. And now this is the switching condition we've already discussed. This, maybe I should say, this will go from arc 1 to the line. Okay, so now we're actually looking at our normal switching conditions that we've already been defining. And if we are, then we'll switch to the line. Okay, then our state 3 is if we're in the line. And now we're going to indicate flag 1 is indicating again that we're in the line. And then our R and Q values, those are the parameters that we defined the line with. And this is exactly why we say that Z1, oh, I should have maybe just highlighted that. The R is defined as Z1. Okay. Oh, I defined it earlier. I meant to highlight that Q1, right? So that these are, know that those are the different ones. Okay, we do want to highlight Q1 here because Q1 is equal to Q2, right? But so we're executing the line until we determine that it's time to switch. This will go from the straight line to arc 2. So this is going to be the first part of the arc 2 is going to be state 4. And as we come down here into state 4, again, this is our defining that we have an orbit, and these are the parameters that define that orbit. And then our switching condition, I want to highlight this. We have a negative sign, right? So in this case, we're saying we want to switch and make sure that we cross over. We first want to make sure we cross over into this side of H3 before we care about our final switch. So this will make sure that we don't switch to the next Dubins parameters prematurely. Okay, so the switching conditions, once this is satisfied, we'll do the second part of the second arc. So this, again, state 5 equals second part of arc 2, right? And these switching conditions, once we've now crossed into H3, these ones, this is just define new Dubins path to follow. All right, so we're executing our next path. So we might do something right, straight. Oh, I did left, straight, right. I think I did that at the beginning of the lecture too. So in this case, there'll be left, straight, right. Or whatever our next parameters end up being. Okay, and there you have it. So we have these two slides are very important. First, for defining defining all the parameters that we care about. And second, defining the algorithm that helps us manage what portion of the path that we're on. And the trickiest, the one part that you may have not thought of is having the first part of the first arc and the first part of the second arc. So it's important that you have that logic in there. Otherwise, you'll be switching prematurely sometimes. All right, so there you have it. Now we have a Dubins path following algorithm.